Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist, the only podcast that combines geochemistry and the tea. And no, we're not talking about the tea that you drink, but good old-fashioned gossip. Our mission is to inspire and to shed light on the topics not fancy enough to talk about at a Congress, but important to delve into. Now, without further ado, I'm your host, Sam Scher, and this week we'll be drinking some scotch while talking with Jason Coumans about Hepworth et al.'s paper on the rapid crystallization of precious metal mineralized layers in mafic magmatic systems in Scotland. Jason is a postdoctoral research scientist at Natural Resources Canada. Jason, welcome to Geochemist.
Thank you for having me, Sam. It's really nice catching up after so many years have passed since being at McGill.
Don't mention it. So, Jason, you were surprised and a little bit shy that I invited you on the show. True, we have history, but right on your LinkedIn, you state that your research interests intersect at computational geology, mineralogy, and geochemistry. How could Geochemist afford not to have you on the show?
Oh, thanks. It really is a pleasure to be on the podcast. Maybe I should change my LinkedIn. But I found the first two very interesting, so hopefully I can provide something useful for the geochemistry enthusiasts out there.
No need for modesty. You never know who you're going to inspire. There are others, I'm sure, out there who cannot wait to hear about Spinel.
Yes.
I think what really defined you as a must-have guest for the show is that you are a geochemist and an igneous petrologist thriving in research. So this is something that our young listeners need to hear about. So just tell us, what's your journey been?
Yeah, so my journey actually started after my first year of undergrad. Like many students, I had a bit of a struggle after first year. So I started a degree in astronomy, actually, because I was fascinated with the vastness of both space and time. But at the end of the first year, I struggled a lot with the astronomy courses themselves, and calculating parallax angles didn't really excite me so much. And so I needed to figure something new out. And I have a good recollection of the moment, actually. I was sitting on the couch and I was talking to my dad, and I was like, Dad, astronomy is not really working out for me. I don't know what to do. And he said, hey, you like camping, you like the outdoors. So, instead of looking up at the stars, what about you look down and do geology instead? It's also vast. You also get snapshots of both space and time, and it's a bit more tangible, and you get to go outside for your field courses. And that was excellent advice. So I switched and I took a couple of geology classes and fell in love with it right away, which I think is a classic geology story. I've talked to a lot of people who've switched into it. Just as they take one or two classes and they instantly get the bug for the rocks.
I mean, I came from molecular biology myself, so, close.
Yeah, almost. Yeah, close.
Yeah, the same.
Yeah, and then so after that, later in the undergrad years, when you start taking the classes like igneous petrology and SEDS and structure, I sort of got drawn to volcanoes, mainly because they represent a lot of the sort of dynamic aspects of geology. And they're also in some of the most interesting places. As you remember, you studied Kawajian in Indonesia. And the fascination with the volcanoes led me to grad school at McGill with John Sticks, who, of course, you know well. And that's where I met you. And you even lent me your printed out, I think it was Francis Alvarez's geochemistry textbook. You remember you lent it to me in some of my classes and highlighted and filled with all of these notes, which I really appreciated.
Oh, yeah. I think I still have that book. Should have made money on it while I could.
Yeah. Yeah, so during the PhD, I got to go on a research cruise and study some underwater volcanoes. where I got to investigate the geochemistry of some glassy lavas and entrained crystals and their melt inclusions. And what I found particularly interesting about doing that kind of research was using the geochemistry of these different parts of the same system. So in this little sample we brought up, we have these glasses, which represent the solidified magma. And then in them are some crystals that the magma carried with it. And in those crystals are little glassy bubbles that, which are kind of like tree rings in amber. They capture little bits of a deeper system. And so using geochemistry on these different parts of the magmatic system and trying to untangle what they all mean, I found very interesting.
Yeah, no, I definitely agree with you there. First of all, volcanoes, amazing. And I was always jealous of your little research cruise. It sounded incredible. But that's something, I mean, I guess when I was first going to university, my dad told me, is like, you got to make sure you can get a job out of school. So that kind of threw out doing a history degree out the window for me. But that's something that I've always really loved about geology, is just that it is storytelling. And then I also love science too. So it's just that combination of the two that's, for me, has always really, made it all work.
Yeah, the storytelling part's amazing, where you can just, look at some rocks in the distance, and you have both the space and the time, and you can say, oh, like in this layer it was high sedimentation, then suddenly there's an ashy layer, and it's like, wow, some volcano must have gone off somewhere around here. And you're trying to figure out where it comes from by looking at the layers. It's really is fascinating.
Yeah, liquor and guessing.
Yeah.
Cheers to that with our scotches.
Cheers to that. Time for another glug, I think.
Yeah, click, click.
Yeah, so it's during this sort of untangling in grad school that I started to become interested in modeling, the mathematical time, not the Abercrombie type. Don't quite have that. Beaver. Yeah, I have a body of knowledge, but not that kind of body.
Oh God.
Yeah, and specifically in the stuff I was looking at, there were chemical gradients in the plagioclase crystals in the glassy lavas that I was just talking about. And this led me down the road of chemical diffusion and diffusion modeling, and trying to understand how certain chemicals may transfer between magmas and crystals, or between different zones of the crystal within the plumbing system of the chain of seamounts that I was studying, which happened to be next to mid-ocean ridges. And it's during this sort of diffusion journey that I started to teach myself how to code, as diffusion problems often require numerical solutions. And this is where my interest in geochemistry and coding kind of merged. And that's what led me to my next place, which was a postdoc in England. And that's where I did some work on developing numerical models for the diffusion of water in silicic melts and the growth of bubbles, which is very dependent on the transfer of volatiles.
I think it's a really good point that you make about coding. And I think that right now, everybody at university should be taking at least one coding course.
Yeah, no, it's a great point. During my journey in coding and numerical modeling, one of the most useful things that I got out of it was just how to integrate data sets from all sorts of different sources. Recent example, in the lab that I'm working on, we have a furnace which is connected to a mass spectrometer, and both of these provide different data sets. The furnace provides temperature with time and mass with time, whereas the mass spectrometer gives us how the concentrations of certain gases will change with time. But they both spit out data with different formats, with different time stamps. And so it can be a bit of a mess to deal with it. But, writing a quick code to take these two different outputs, merge them together and integrate them, it means that you can plot multiple things with multiple variables much more easily. And now with the proliferation of open source software and modules that you can import into languages like Python, you can do all sorts of things with, merged and organized data sets. Just as an example, QGIS speaks to Python. So if you have chemical data and spatial data, you can integrate them quite easily. Although I haven't played with it myself, so maybe I'm saying it's easier than it actually is.
I don't code in Python. I use R, so I'm not quite sure about that. But having taught myself QGIS in the past few weeks, QGIS is very easy to learn and it's fabulous. And everybody also should be using it. I am not getting any money for plugging QJS. All right, so that's really interesting. And I guess just, throughout this whole journey, I'm just wondering, do you have any tips or advice to give our listeners that really want to break into research or academia?
Get involved with research and something you're interested in as soon as you can. Often professors at universities will take on undergraduate lab assistants or field assistants to help with all sorts of different aspects of your research. So this is a great way to learn about what goes into research. You get to speak with research scientists in a non-lecture environment. So you can ask all sorts of questions and pick their brains about things that you would not get in a lecture environment. And most importantly, you kind of learn what goes into getting the data required to progress science. Not just how much you need, but how to answer questions, what sort of constitutes a publishable body of knowledge. And if you like it, try out different projects as well, especially if you start early. And this will give you a variety of experiences as research and different aspects of it. Maybe you'll enjoy something you didn't think you would. And I guess finally, ask lots of questions, read the new research that's coming out. Being a research scientist is all about asking why and trying to find the answer to it. So asking as many questions as you may bring up more questions, but that's a good thing. And that's how research and science progresses.
And I think even for those people that are interested in pursuing industry-related fields like mineral exploration, mining, petroleum, it still is very applicable, that whole part about learning how to ask questions, because that's something that I saw time and time again working in more of a business development field. And a lot of times people would want to use the product, but they didn't actually know why. They're just like, no, we want to use hyperspectral. And it's like, okay, well, what's your question? And it's like, because we want minerals. And it's just, well, that's not actually a question. So that's actually a really good point that you could probably just expand the way you look at, your worldview even by doing maybe perhaps a research project like that. So it's a really good point.
Yeah, no, that's a great point. Like, even if you don't end up going into research, just learning how to ask why is helpful in any situation.
That was a really long and interesting journey. And I think, though, honestly, a lot of our students probably will get a ton out of that. So thank you for sharing all of that. I think particularly your dad's advice was very helpful. Maybe mine, not as much, but yours.
Yeah, my dad's very wise.
This brings us to our next segment. Maybe you have some better tea than, sharing stories about our favorite song in 2011 being Moves Like Jagger.
Fair, though. That song was an absolute bop.
Yeah. I mean, there's nothing that quite made you shoot like a hole in one when you're playing pool, drinking Labatt Blue, like Moves Like Jagger. There's really no point in revisiting Montreal. That just is just a little bit too maybe boozy for our young listeners. Maybe for some of our older listeners as well. So what else you got?
Yeah, so I guess one of the kind of more serendipitous things that have happened in my geology journey was when I was at a conference for volcanology in Kagoshima, Japan. As we were in lecture halls listening to this, we hear a slight rumble, and you go outside and suddenly there's an ash cloud in the air, and the volcano nearby has gone off. Nothing too crazy, but still it's spewing ash in the air that's coming down over the city. And so all of these nerdy volcanologists are leaving their talks to rush out and see the volcano erupting, because where else could you be at a volcano conference and have a volcano going off? And I remember, I was with my supervisor at the time, John, and a few other grad students and a postdoc, and we're all rushing over there, driving over there, and everyone's out there trying to collect as much of this material as they can with what they have on you. Like, I remember Brandon and Gregor were holding out a bandana, just trying to collect this stuff and putting it in. Somebody dumps out their water bottle and was like, okay, put it in this so that we can seal it and take it home with us. And so, because you have, the idea being like, screw danger. Let's just collect as much of the stuff as we can for the science. So I thought that was a kind of a sort of serendipitous time to be a volcanologist, I think.
I can't even imagine. I can see myself participating in said thing, but I think I would have really enjoyed the nerd reaction more than anything.
Oh,
just,
it was
the pandemonium, not just of people wanting to be safe, but people just, being like, oh my God, I must see this.
Yeah, usually people run away from them, but in this time you had, a whole flock of people running towards them, which was I will say it wasn't at the time. It wasn't too big an eruption, so nobody got seriously injured or anything
Okay. Well,
that I know
that's
of,
nice to
anyways.
know. Yeah. I guess that should have been our disclaimer to start with,
Yeah,
but everybody was safe.
no one was injured in this recording of geochemistry.
Well, we don't know. I mean, we still have, some questions to go through. So amazing. That said, let us now move on to our geochemistry portion of the podcast. You chose a paper, which I was a little bit surprised by. You told me that you're going to pick a nice short nature paper. And I was thinking to myself, okay, great. I can do this. This will be easy. This will be straightforward. But I forgot. Nature is always just dense, and it's just everything. And just, the highest level is in nature. Your paper was on the rapid crystallization of precious metal mineralized layers in mafic magmatic systems by Hepworth et al. The other thing that I got from when you were first suggesting a paper is you were a little apologetic that wasn't more exploration mining focused, but this paper actually blends pretty well your research interest with something that's actually particularly mining focused. In that sense, what drew you towards platinum group elements and these mafic magmatic systems?
Despite not currently being a volcanologist, I still do have an interest in magmatic systems and their genesis. And in fact, my current research for Natural Resources Canada involves chromites from the Ring of Fire deposit in northern Ontario. When these chromites, which often form seams in layered intrusions like the Bushveld in South Africa or the Stillwater in Montana, and rum is no exception to this. Except one of the nice things about rum is it's much younger and very well exposed. And, from platinum group elements and chromium, which is from the chromite seams and where my interest lies, are also emerging as critical minerals during our transition to the green economy. Chromium specifically is largely imported into North America, but here in Northern Ontario, we have a large deposit, the Ring of Fire one. And so if it's developed, it could become the major source of chromium in North America. And then we wouldn't have to rely on importing it for, say, our automotive industries, which are huge in the US-Canada trade.
Well, I did not know we would be getting into a supply chain discussion, but a nice little pivot there. But that's really interesting in how you selected the paper, because at first I was just like, oh my goodness, where do we go from here? But it was a really fascinating paper. And then, as you point out, the fact that the Ring of Fire can be developed and having that source of chromium here in North America, that would be something that definitely of interest considering current events.
Yeah, to put lightly.
Yes. Immediately jumping out in this paper to me was, in the abstract, the authors discuss a cooling temperature of 1 degree a year in these mafic magmatic systems. Based on your experience working with volcanoes, audience, I think at this point we've mentioned enough, this guy's a volcanologist, or in his prior life, volcanologist. I'm just wondering, is this temperature decrease reasonable in the sense that, when you have, say, the Pacific plate is moving at 2 centimeters a year, really that's just an average just with each event where it, subducts. So is this temperature reasonable?
Oh, no, that's an interesting point to bring up, especially with these sort of large magmatic intrusions. So to sort of give an idea of cooling rates and sort of to put it to something tangible in scale, like for something that's erupted out of a volcano, so ash clouds like the one at the conference, those cool at the sort of 0.1 to 10 degrees per second. So really quickly, as you would expect, as it was touching air. So 1 degree to C per year might seem slow, but when you're thinking of a large mass of magma, beneath the surface where the temperatures are a bit warmer as well, it could take, something that's hundreds of meters thick and kilometers across could take thousands of years to cool. So you're looking at, fractions of a degree per year. And if they're placed in either warmer rock, it could be longer. And this is sort of thinking about how if you emplaced a large amount of hot material and, you have to kind of cool it from the outside in. And yeah, things like convection, like, you think of your stove and you have your water bubbling and the movement of hot material to the surface helps remove the heat. And some of that is thought to have occurred in these in the past. Then it could take millions of years to cool such a slow thing. But in our more recent studies of these large intrusions is thinking of something a bit different. So 1 C a year is actually quite quick when we think about these large intrusions. Previously, it's been thought that it's millions of years to cool these things. So these temperatures that they're claiming of 1 C a year is actually quite quick. But that is related to their sort of new idea of how these large mafic systems sort of keep going.
Because that was exactly kind of my follow-up here, was that this is kind of closure temperatures within tens to hundreds of years. And I was like, whoa, 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 am I misinterpreting this? Or what exactly were they saying here?
What they're talking about is in these rapid crystallizations, and instead of having a large body of magma that's maybe cooling slowly beneath the surface, instead what they're thinking is you have multiple pulses of smaller volumes of magma that are then cooling much more quickly. And so the longevity of these large intrusions, it's kept going by these sort of small but rapid injections that are on much shorter time scales, much shorter length scales.
That's super interesting.
Yeah, and a lot of the more recent work is, we think of a magma reservoir in your head and you're like, okay, this must be mostly liquid, right? But actually we know from seismic tomography and from investigations of intrusions like Rum or other ones like Skaregard in Greenland that these things are actually made of something called a crystal mush. And so it's actually what we think of as a magma reservoir is actually mostly crystals with melts between it. And where we think the melt comes to erupt small amounts of melt from this large body of something that's mostly solid somehow gets close to the surface and then becomes eruptible.
So I learned a new word, bifurcate. I'm not sure if I'm pronouncing it the right way. So for everybody in the audience, bifurcate, which simply means to divide into two branches or parts. I think you're going to know where I'm going with this. And it ties into my question about these long-lived systems. And this paper claims, as we were just chatting about, that Rum in Scotland have magmatic pulses and cooling last tens to hundreds of years. But now we're starting to really see how we're getting the concentrations of PGE and the chromium seams that this intrusive complex warrants. Can you expand on my high-level overview and really put the science back into that?
Yeah, one of the more interesting parts of this paper was how they sort of explained how are you getting the PGE concentrations and how are you getting these chromite seams? Where are they coming from?
Exactly.
And so part of their sort of investigation was focusing on these small areas or small lenses where sometimes they do bifurcate, where it starts in one horizontal layer and then branches or splits into two. It sort of indicates some kind of fluid flow or melt flow through the system. And so one of the big discoveries that they were making is that you get these hot injections of something that's primitive and it interacts with the rock around it and flows through. And these hot melt can sort of melt away the crystals that are in this sort of warm mush. So when your mush is surrounded by some fluid, it's easy for these hot intrusions to percolate through them, but it's also easier then and requires less energy for this hot melt to dissolve the crystals around it. And from this, they're taking in sort of some calcium and some aluminum, and then you're dumping out this chromite spinel. But as a side effect of this, you're also grabbing up all of the goodies. So, your platinum, your palladium, your rhodium, you're sort of collecting all of these goodies from the mush that it's percolating through, and then you're dumping it out of the system as sulfides. And as a consequence of these repeated injections of hot material into this, I'm going to call it warm crystal mush, you're able to concentrate not only the platinum group elements in sulfides, but you're dumping out chromite, which is a major source of chromium, which, as we discussed earlier, is important in the automotive industry for stainless steel, for example.
It's interesting, it's not that I haven't heard similar things before or had some similar discussions or anything, but this is definitely really interesting, and I really like the way that they were able to put it in the paper. Very dense reading at first, but after reading it the second time, and now you giving me this igneous petrologist view of what exactly they were saying, I think, and I hope it comes out for the rest of you guys that are listening, this is all starting really to crystallize in my mind.
Yeah, good one.
So there's a lot of talk about the work that the authors did with strontium isotopes. Can you explain to our listeners what the authors used the strontium isotopes for and how they ultimately impacted the conclusions that were made? That the conventional wisdom that PGE-rich chromatites crystallize from the bottom of the magma chamber up is not appropriate at RUM.
That's a very interesting point. And key to this study was their investigation of the crystals within the chromite seams. What they discovered was that within the chromite seams, the individual crystals had all sorts of different chemical zones. And this was different than the surrounding rocks, both above and below. And so what they did is they took a tiny little drill with a micron-sized bit, and they drilled away out of these zones, of these heterogeneous zones of the crystals. And then they did an isotopic analysis of it, as well as your conventional geochemical microprobe analysis to see how the isotopes varied in these crystals. And what they discovered is that they were quite heterogeneous, which is suggesting that the system has not had a lot of time to re-equilibrate, which again is what's supporting their rapid crystallization and cooling timescales, but also it's supporting their implication that there's lots of repeated injections of material that are grabbing isotopic signatures that have already been locked in from all over the place, that have been locked in from different times, and these melts are just grabbing them, and because of the short timescales, they're being preserved in the crystals. And so how does this impact the conclusions? Quite a big one. Traditionally, it was thought that these large intrusions sort of crystallized from the bottoms or the sides, where the thermal gradient is the largest. So you lose heat to the exterior rock and you crystallize some material and it settles to the bottom. But in this conclusion, they're suggesting that, well, no, instead of that happening, you're getting these intrusions of lots of small volume melts, and they're picking up stuff from all over the place and crystallizing in place. So it's quite a different model than what was originally thought.
I think that was really well said. It was much easier for me to unpack that than to read it in the paper. So thank you for that. As a research scientist, how do you feel overall about the constructs of the study? The microprobe work they did, the isotope work they did, temperature modeling, discussion points, conclusions reached. Like, what are your general feelings about the study?
Yeah, it's overall it's a great study, and they're sort of adding another point to the studies of crystal mushes and magmatic systems, which are becoming more and more important to how we understand magmatic systems in general. And so their microprobe work was excellent, and the isotope work I found quite interesting. Using the micro drill to pull out material from different sections of the crystal. This is because you might think of doing it with the laser ablation, but with the micro drill, I think you can actually do the isotope study, which you can't do with laser ablation. So that's quite interesting. Now there are some problems, like your micro drill is. Even if you're 50 micron or 100 micron bit at the bottom, you might overlap a couple of zones, and you might have sort of a mixed signal. But they address that in their paper, and they make that quite clear, and they're quite transparent about that, which is good in a study. If there are things that could kind of fudge data, you want to make sure that you're transparent about it so that people might understand. Yeah, and so with the temperature modeling, there's some research out there looking into, we were sort of discussing about the longevity of large magmatic systems. And this is not just important for large igneous intrusions like the one we're talking about, but think of places like Yellowstone, where if that thing goes off, you have the possibility of a nuclear winter type of thing where the ash is in the atmosphere. So you really want to understand sort of how long these things are around for, how the melt gets out of them. And there's a lot of new research surrounding crystal mushes as we're starting to understand that the magma reservoirs beneath these large volcanic systems are actually mostly crystals. And we want to understand, well, okay, how does melt interact with the crystals? How do you liberate melt from this predominantly solid material? So how do you turn something that's, 60% crystals into something that's effectively all melt and then erupt it? And studies like this, where they go out to the field and they find these examples of melt percolation, and they look for these examples of where a system's kept around by repeated injections of material. This is all very important to understanding how large magmatic systems remain long-lived. But in terms of thinking of platinum group elements, which are going to be more and more important as we transition to the green economy, understanding the mechanism behind where we can collect and dump out these important sulfides, that could be important for looking for targets in the future. So say we find another large igneous province, we could look at this research and say, hey, these chromite seams which dump out from reactive flow, we need to look for this characteristic, this geochemical characteristic. Let's go out and find them. And then if we do, and we can find the sulfides that we're interested in, then that could help.
Those are really interesting discussion points, and a bit more than I was expecting. Very cool. I think where I want to end up with you, my last question that I'm going to have is something that I've been chatting about more and more with other geochemists and geoscientists in general, is that there seems to be a falling standard in some journals where once it took months upon months, years even, of editing and revisions, and now people are finding that this process has just come to be, in some cases, just a matter of weeks. So do you have any comments on this at all?
Yeah. So one to be wary of are predatory journals, and we all sometimes get these emails in our mailbox, but they are quite and they're proliferating quite broadly. A good piece of science requires a fair amount of time to give it its due diligence. As reviewers, we have to assess its robustness. We have to look at the methods, make sure they were done correctly. We need to make sure we look at the data and that is presented. Was it something for geochemistry that might be important to something like standards? What standards were used? These are all things that we have to investigate in quite a fair amount of detail. And a lot of these predatory journals, they promise, quick turnaround times, but there's no way that a good piece of science can be given its appropriate investigation in such short time frames. And on top of that, add to that the revisions for journals they're done by scientists in their spare time, and they're not paid for them. And the scientists are primarily at universities now, and they're even having less and less spare time as the teaching loads become greater and greater. And so it's harder to find reviewers. So with that's also potentially dropping down the quality. And reviewers aren't paid. We do this out of our duty to science and for progressing things. And I guess I could use this as a beware for predatory journals, both submitting to them and reading science from them. And it becomes difficult as a researcher, because now we have to take into account the source of what you're looking for. And you don't want to implicate that bias, and you want to make your own judgments yourself. But more, so I'm going to use the word sketchy science that hasn't been appropriately reviewed is finding its way through the cracks and swamps out the good stuff just because it's being pumped out quicker for the sake of citations. That's bad for everybody. You're drowning out the good stuff with noise, essentially.
I think you make some really great points, and I really thank you for sharing your opinions on this. That said, I really want to thank you for stopping by the show and having such a great chat with us. I definitely learned some interesting things about crystal mushes that I haven't thought about since, well, a long time. I haven't really worked so much in PGE, so maybe that's my problem. I really hope that you guys at Natural Resources Canada enjoy studying those spinels.
Oh, we do so very much.
All right. Thank you.
Thank you. Bye now.
All right, guys. Well, thanks so much for joining us this month. And next month, we look forward to seeing you again. And you can check out our webpage at www.geochemist.com to look up and see what our next shows are. Thank you.